somewhere past the edge of everything humanity has ever mapped. A machine older than the internet, older than cell phones, older than most of the people currently. Keeping it alive, sent a signal back to Earth that took 23.5 hours to arrive. 23.5 hours for a whisper of electricity to cross 15 billion miles of nothing. And when that signal finally landed in a control room in Pasadena, the engineers reading it did not see triumph. They saw a warning. Something on board had gone wrong, unexpectedly, silently. Nobody had seen it coming. This is the story of what happened next, and why it matters more than almost anyone is talking about. To understand why that warning mattered, you have to go back to a decision nobody questioned for almost 50 years. In 1977, NASA launched 2 machines into space with a job that was supposed to last 4 years. Fly past Jupiter, fly past Saturn, take pictures, send them home, then go quiet forever, drifting into the dark like every other piece of hardware humanity had ever thrown into the void. Nobody expected these 2 probes to still be transmitting data in 2026. Nobody expected them to become the only human-made objects to ever leave the bubble of our solar system and survive to tell us what interstellar space actually feels like. But here's where it gets strange, because Voyager 1 and Voyager 2 didn't just survive. They kept going, decade after decade, past the point where every engineer who built them assumed they would already be dead metal drifting in silence. What most people are not seeing is that this survival was never guaranteed, and it was never permanent. Every single day since 1977, a process has been quietly ticking away inside both spacecraft, a process nobody can stop, slow down, or repair from 25 billion kilometers away. Each Voyager runs on something called a radioisotope thermoelectric generator, essentially a nuclear battery that converts the heat of decaying plutonium into electricity. There's no sunlight to rely on out there. At Voyager's distance, our sun is just another star in the sky too, faint and too far to power anything. So the plutonium has been doing all the work alone for 49 years. And plutonium, like everything else in the universe, obeys a law nobody can negotiate with. It decays. Every year, both spacecraft lose roughly 4 watts of power. Read that again. 4 watts, less than a household light bulb. That is the entire margin standing between still exploring and gone forever. For most of Voyager's life, that slow bleed of power was manageable. Engineers could shut off an instrument here, heater there, and buy themselves another year, then another, and then another. It became almost routine. In September 2024, Voyager 2's plasma science instrument went dark. In February 2025, Voyager 1's cosmic ray subsystem followed. In March 2025, it was Voyager 2's low-energy charged particles experiment. Each shutdown was planned, deliberate, forecasted years in advance. The team knew exactly which watt they were sacrificing and exactly what they were buying with it. This is not chaos, this is strategy. Slow, careful, unglamorous strategy, executed by people who understood they were rationing the final years of a machine that had already outlived every prediction ever made about it. But then came February 27th, 2026, and this is where everything changes. On that day, Voyager 1 was performing something engineers call a routine roll maneuver, a basic, uneventful repositioning that the spacecraft had executed thousands of times without incident across its lifetime. Except this time, something didn't behave the way it was supposed to. The spacecraft's power levels dropped unexpectedly, not on schedule, not part of the plan, a deviation out there in the freezing dark, 15 billion, miles from anyone who could physically intervene. Think about what that means for a moment. There is no repair crew. There is no backup system waiting on standby. There's a team of engineers on Earth staring at telemetry data that is already 23 hours old by the time they receive it, trying to diagnose a problem on a machine they cannot touch, cannot see, and cannot reach, in less than a full day of radio travel in either direction. Whatever happened during that roll maneuver, the ripple effects were immediate and impossible to ignore. The response came fast, and it was brutal in its simplicity. On April 17, 2026, engineers at NASA's Jet Propulsion Laboratory sent a command across the solar system, across the heliosphere, out into true interstellar space, instructing Voyager 1 to shut down its low-energy charged particles instrument, known as the LECP. This was not a minor sensor. This was one of the defining scientific tools of the entire mission, an instrument that had operated almost without interruption since the day Voyager 1 left Earth in 1977. It was the LECP that helped scientists first confirm Voyager had crossed the invisible boundary, out of our solar system and into the true space between stars. According to the instrument's own principal investigator, Matt Hill, working out of Johns Hopkins Applied Physics Laboratory, this was the tool that let scientists sense the changes in the region around the spacecraft. The very changes that told humanity the exact moment we had left home behind. And now, in 2026, it had to be sacrificed. Not because it broke, because there simply was not enough electricity left in the machine to keep it running. Sit with that for a second. Out of the 10 scientific instruments Voyager 1 originally carried into space, only 2 remain active today. 2, a magnetometer and a plasma wave subsystem. That's it. That is the entire scientific output of humanity's most distant machine, reduced from 10 working eyes and ears to 2, not because of failure, not because of damage, but because of a slow, mathematical, unstoppable decline in electricity that has been running since the day it launched. The real story here is not a single dramatic failure. It's something colder and, in its own way, more unsettling. It's entropy, playing out in real time, 15 billion miles from home, and there is nothing anyone on Earth can do to stop it. They can only decide, instrument by instrument, watt by watt, what dies next. And here's where the story stops being just about machinery and starts being about the people making these decisions. Somewhere in that shutdown sequence, there was a detail that almost nobody outside the mission noticed, but once you hear it, you cannot unhear it. Engineers deliberately left a tiny half-watt motor running, the motor that rotates the now dormant LECP sensor. They kept it alive on the smallest possible trickle of power, for one reason only, in case the instrument could ever be turned back on, in case some future fix bought them enough electricity to resurrect a sensor everyone had just declared dead. Stimatios Krimigas, one of the instrument's principal investigators, later wrote in an email that after the supplemental heater was switched off to save power, the mechanism's temperature dropped to minus 62 degrees Celsius, and astonishingly, it kept working anyway. His own words were that this is the stuff dreams are made of. Read that again. A piece of 1970s engineering, freezing in the vacuum beyond our solar system, still turning, still functioning, decades past anyone's expectation, on a fraction of a watt. But sentiment doesn't pay the electricity bill. The math is still the math, and the math keeps getting worse. This is where the mission's own leadership stopped sugarcoating the situation. Suzanne Dodd, the Voyager project manager at the Jet Propulsion Laboratory, has openly acknowledged that if the team does not act, and act now, on each spacecraft, the probes would have only a few more months of power before mission controllers would be forced to declare the entire program over. Not years, months. Think about what that timeline actually means. A machine that has survived for nearly half a century, that crossed a boundary no human object had ever crossed before, that has become a permanent artifact of human exploration, drifting through the galaxy long after its builders are gone, could have gone silent within a matter of months if nobody intervened. That is not a distant, abstract risk. That was the reality facing engineers in early 2026, so they gambled. And the gamble has a name that sounds almost too dramatic to be real, except it is completely, officially real. NASA calls it the Big Bang. Here's what most people watching from the outside don't understand about this plan, and why it deserves far more attention than it's getting. The Big Bang is not a single small fix. It is a coordinated, simultaneous swap of multiple power-hungry components across the spacecraft, replacing them all at once with lower power alternatives in an attempt to squeeze out every remaining watt the aging hardware can offer. Specifically, engineers plan to shut off heaters that have kept the spacecraft's thruster fuel lines from freezing solid, and in the same maneuver, switch on other, more efficient devices designed to perform that same protective function using a fraction of the electricity. If it works, the team believes they can recover something in the range of 10 additional watts. 10 watts in a system where every single watt now represents the difference between operational and permanently dead. But here's the part that should make your stomach drop a little. If this maneuver fails, if those fuel lines are allowed to freeze even briefly during the transition, the spacecraft loses the ability to fire its thrusters, which means it loses the ability to keep its antenna pointed at Earth. And a Voyager probe that cannot aim its antenna at Earth is a Voyager probe that can no longer talk to us at all, regardless of how much power it might still have left inside it. This is not a routine software patch. This is open heart surgery performed by a remote control on a patient 15 billion miles away, where the surgeons cannot see their own hands, where every single command takes nearly a full day just to arrive, and where a single miscalculation could end the mission permanently, instantly, and irreversibly. And here's the detail that turns this from a technical curiosity into genuine tension. NASA did not attempt this maneuver on Voyager 1 first. They couldn't afford to. Voyager 2, slightly closer to Earth and carrying a marginally larger power reserve, was chosen as the test subject, scheduled for May and June of 2026. Voyager 1, the more fragile, more depleted, more historically significant of the two, was told to wait. Wait and watch, while its twin absorbed the risk first. Think about what that means for the team running this mission. They built a hierarchy of sacrifice into their own rescue plan. They chose which spacecraft would take the first hit, knowing that if the maneuver went wrong on Voyager 2, they would learn from that failure before ever risking it on Voyager 1. Only if the Voyager 2 test succeeded would engineers move forward, attempting the same procedure on Voyager 1 no earlier than July 2026. And if that attempt worked, there was a possibility, not a guarantee, a possibility that the LECP instrument, the very sensor sacrificed back in April, could be switched back on. Brought back from the dead, powered by watts, scavenged from a desperate engineering maneuver performed on a machine older than the concept of a smartphone. This is the part of the story that mainstream coverage keeps glossing over, treating it like a routine maintenance update instead of what it actually is, a live, ongoing gamble with humanity's furthest reaching instrument, happening right now with an outcome nobody can predict from Earth. As of the most recent confirmed engineering updates, Voyager 1 sits more than 15 billion miles from Earth, so far away that a radio signal traveling at the speed of light needs roughly 23.5 hours just to reach it, and then another full day for any response to travel back. When engineers sent the shutdown command for the LECP instrument, the deactivation process itself took a little over 3 hours to complete, once the signal finally arrived. Now imagine the Big Bang maneuver, a far more complex, far riskier sequence of simultaneous swaps, being executed under that same brutal communication delay. There is no room for a quick correction. There's no room for a do-over in real time. Whatever happens during that maneuver happens alone, in the dark, with Earth completely unable to intervene until the consequences are already locked in. And this is where the deeper, quieter tragedy of the story sits, the part that never makes it into a headline. Somewhere in the sequence of decisions being made right now at the Jet Propulsion Laboratory, a team of engineers, some of them not even alive, when Voyager 1 launched in 1977, are being forced to choose which pieces of a nearly 50-year-old spacecraft get to survive and which get switched off forever. Every shutdown is permanent. Once an instrument goes dark under these conditions, in that cold, in that isolation, there is no confirmed guarantee it will ever function again. Motor or no motor kept spinning on a trickle of standby power. The team is not just managing a spacecraft. They are managing an ending, trying to control the pace and the shape of it, trying to decide what humanity gets, to keep learning before the silence becomes permanent. Here's what most people don't realize about what's actually at stake scientifically, buried under all the engineering drama. The instruments still functioning aboard both Voyagers are not replaceable. Measurements of what exists out there, the structure of the space between stars, the pressure fronts, the shifting density of particles in a region no probe launched in the 21st century has come remotely close to reaching. Everything Voyager still sends back is data that literally cannot be collected any other way, by any other mission for years, possibly decades into the future. Every watt saved by the Big Bang maneuver is not just extending the life of an old machine out of sentimentality. It is extending humanity's only direct sensory connection to a region of the universe we have only ever touched once, and may not touch again for a generation, if ever. There's a symbolic marker sitting on the calendar that makes all of this even more charged. In November 2026, Voyager 1 is projected to cross a milestone known as 1 light day from Earth, a distance of approximately 25.9 billion kilometers. The exact distance light itself travels in 24 hours. It will be, in some ways, a strange kind of anniversary, a number that sounds abstract until you actually sit with it. A signal leaving Earth right now, traveling at the fastest possible speed anything in this universe can travel, will need a full day just to catch up to where Voyager 1 will be. And engineers are trying to keep that spacecraft alive, functioning, still listening, still speaking as it crosses that threshold, all while gambling on an unproven power-saving maneuver that could either extend its life for years or accidentally cut it short before it ever reaches that symbolic distance at all. So where does that leave us right now in the middle of this unresolved story? As of the most recent confirmed updates, the Big Bang procedure was scheduled for testing on Voyager 2 through May and June of 2026, with a decision on whether to attempt the same maneuver on Voyager 1 expected no earlier than July. Whether that test succeeded, whether Voyager 1 will actually undergo its own version of the maneuver, and whether the sacrificed LECP instrument will ever hum back to life 15 billion miles from home remains genuinely uncertain, still unfolding as engineers on Earth wait out day-long delays between every single command and every single response. Nobody, not the mission managers, not the instrument scientists, not anyone watching this unfold from the outside, can say with certainty how this ends.